Hey, what's up, everybody? It's Miss Brothers. Hey, let's take a look at these Charles Law problems from our practice number 2. So if you look at this, and this one's really straightforward, unlike the first practice where we did some conceptual stuff, this is almost entirely just math related. So apologies if the video is a little blurry up here. We'll do the best we can to kind of mitigate that as we go. So we're going to go ahead and just get started on this. Also know, you guys, I will be using our little help tool that I gave you. And again, we're going to be focusing on Charles Law, so that's going to be that series of formulas that's in the middle of the page right here. Okay, let's get started. It says a sample of nitrogen occupies a volume of 250 milliliters at 25 degrees Celsius. There's a bunch of information right there. So we've got a nitrogen, so it's a gas at this point with a volume of 250 milliliters at 25 degrees Celsius. And we want to know what volume, we don't know that, will it occupy at 95 degrees Celsius. So our first volume is 250 milliliters. We can go ahead and label that as V1. We've got our first temperature at 25 degrees Celsius. We're going to label that as T1. And what volume will it occupy? So that's going to be our V2, and that's the thing we don't know. Will it occupy at 95 degrees Celsius? And that's going to be our T2. So again, the first thing we have to do is we have to go ahead and convert these temperatures that are currently in degrees Celsius, and we have to convert them to Kelvin. So we're going to do that first. So T1, which is 25 degrees Celsius plus 273. So our T1 is going to be equal to, and we'll go ahead and just grab ye old handy calculator here. 25 plus 273. That gives us 298 K. I'm going to go ahead and just kind of block that off to remind me that's my T1. Now I have to find my T2 in Kelvin. My T2 is at 95 degrees Celsius plus 273. If I do the math on that, 95 plus 273 is 368 K. I'll just go ahead and section that off, and I've got my nice little temperature section there where I've done my conversions to Kelvin. Now, remember, I'm trying to find my V2. That is the thing that I do not have. So I'm going to come over here to my little help document. Remember, I'm in Charles Law right here, and the variable that I'm trying to find is my V2, which is right here. And so if I look over on this little section right here, the formula that I need to use is going to be V1 times T2 over, and that's that slash mark, that forward slash that you see right here. That's the same as a division sign, and that's going to be over T1. So we're just going to keep that kind of close by here as we go ahead and put this together. So it's going to be, again, using this formula, V2 equals V1 times T2 over, and that's the little slash mark here, over T1. So this is the formula that I got right from here. So this formula that you see here is the same as saying this right here. So now that we have the formula, we can start going in and plugging in our numbers. So V2 equals V1, and we determined earlier that V1 is 250 milliliters, okay, times our T2, which is this T2 right here that we converted to 368 K, over T1, which we figured out is 298 K. And remember, you guys, we're converting to K because when Jacques Charles, started putting this law together, he was using absolute temperature as the way that he was determining that relationship between volume and temperature. So our V2 equals, and what we're going to do is we're going to go ahead, remember our order of operations. We're going to do our multiplication at the top first, and then once we get that answer, we'll divide that answer by 298K. So 250 times 368 is 92,000. And remember, we are going to go ahead and cancel out the units that we are doubled up here. So that's going to be Kelvin because we want to get a volume, which means we're going to need milliliters. So that's going to be 92,000 milliliters over 298. So our V2 equals 92,000 divided by 298, and that equals 308.723 milliliters. And we're going to go ahead and circle that, and that's going to be our volume. And then we have to ask ourselves, does that make sense? Because if we recall that if our temperature increases, our volume should also increase. Well, did our temperature increase? It did. It went from 25 degrees Celsius to 95 degrees Celsius. And our volume went from 250 milliliters, and our new volume is now 308.72 milliliters. So that's a good indication of the fact that we've done this correctly. A couple of things to point out as we go through these problems. Notice, you guys, how I am showing you my temperature conversions. That's going to be a big deal when it comes to scoring points on a test. You want to make sure you're doing those temperature conversions. You'll notice that I've included the units throughout the entire problem, and I've also taken the time to show you that I've canceled units, and that shows you how I end up with my final units. This unit makes sense because milliliters, because we are trying to find a volume. So that's problem number 1. Let's go ahead and do problem number 2. Now, I am going to do all the problems for this. If at any point you say to yourself, hey, I know how to do this, I don't need help, you can always stop the video and move on. But if you want to keep working along, you most certainly can. Okay? So number 2, oxygen gas is at a temperature of 40 degrees Celsius. I'm going to underline that and just remind myself that that's a temperature, but it occupies a volume of 2.3 liters. To what temperature? So we're trying to find a temperature here. Should it be raised to occupy a volume of 6.5 liters? So this is going to be, this 40 degrees is going to be our T1. This first volume that we have here is going to be our V1. We're trying to figure out our T2 if we have a new volume of 6.5 liters, and that new volume is another way of saying our V2. So it looks to me like we're going to have to convert our T1 to Kelvin, because right now it is at Celsius. Let's go ahead and do that. So T1 equals 40 degrees Celsius plus 273. So our T1 equals, so let's go ahead and do that, 273 plus 40 equals 313K. And again, I like to just put a little barrier there, so that just reminds me that I'm doing my temperature calculations over here. And now what I need to do is I need to figure out how I'm going to get my T2, because that is what I'm looking for right here. So I'm going to go back to my little handy tool here. I'm going to go back to Charles' law, which is right here in the middle, and I'm going to find the variable T2, which is the one down at the bottom. It may be a little hard to see from the video, but what we have is, if we follow this formula, it's V2 times T1 over, there's my forward slash, V1. So if I'm going to write that out, it's going to look like this. T2 equals V2 times T1 over, and again, that's what that forward slash stands for. When you see the forward slash, that means over V1. So now let's go ahead and plug in what we have. So our T2 equals our V2, which we determined was 6.5 liters, times our T1, and again, remember, we're not using degrees Celsius. We are using our calculation of K, which is 313K, over our V1, which we determined was 2.3 liters. 2.3 liters. Again, our order of operations tells us that we're going to go ahead and multiply our numbers on top, our volume and our temperature on top first, get that answer, and then divide that answer by 2.3 liters. So let's go ahead and do that. So 6.5 liters times 313K is 2,034.5. Now again, we have to note what we're going to cross out here, or cancel. We're going to cancel liters because we are looking for a temperature, so we know that this should be K over 2.3. So then our T2 equals, and we're going to go ahead and do our division there, that 2,034.5 divided by 2.3 equals 884 point, and we're going to go ahead and just round that up to 884.6 K. And if we wanted to, we could go one step further, and we could convert this back to Celsius if we wanted to, by simply subtracting 273. All right, on to number 3. Here we go. Hydrogen gas was cooled from 150 degrees Celsius to 50 degrees Celsius. So we're cooled, and it looks like we have two different temperatures there, 150 degrees Celsius and 50 degrees Celsius. Its new volume is 75 milliliters. What was the original volume? All right, so this is a little bit different because right now we have to find its original volume. So we're looking for the T1 right there, okay? Its new volume, new meaning our T2, is going to be 75 milliliters. So, oops, looks like I messed that up. So that's actually supposed to be volume is V. Silly me, sorry. V1, and these are our temperatures. My goodness, that was a big mistake. It's a good thing I'm checking my work. All right, so then we cool from 150, so that's my T1, 250 degrees, that's my T2. And again, this is going to be my original volume, V1, my second volume, V2 right there. And yeah, so the first thing we have to do obviously is to convert our temperatures because neither of these temperatures are in Kelvin. So let's go ahead and take some time to do that. Our T1 is 150 degrees Celsius plus 273. And if I take the time to use my handy dandy calculator to do that, 150 plus 273 is 400. So T1 equals 423 Kelvin. We'll go ahead and section that off. You know how much I like to do that. So, because again, it keeps me organized, head of the game. That's what I want. And as far as my T2 is going to be 50 degrees Celsius plus 273. So my T2 equals, again, 50 plus 273. Is 323K. So I have calculated and done my conversions for both of my temperatures, which is awesome. And now, sorry, I'm adjusting my microphone here because it's bugging me. Oh, that's better. Good. All right, and so now the one that we don't have is we don't have our V1. So now we have to figure that out. V1 equals. And if I go to my little help tool here, and again, we are working in our Charles Law section, which is the middle section. We are looking for our V1. And if we look at the top, we see it here. And V1 is the same as saying V2 times T1. I've got my forward slash right here, which is the same as saying over or divided by T2. So let's go ahead and write that out. So V1 equals V2 times T1 over T2. So V1 equals, and if we plug these in, our V2, which is 75 milliliters, times our T1, which we determined to be 423K, over our T2, which we determined was 323K. So our V1 equals, and again, we're going to go ahead and multiply what's on top first. So we're going to take that 75 times 423, and that's going to be 31,725. Now, as far as the unit, remember, this is a unit of volume, so we know that our final unit's going to be milliliters, and we can cancel out our temperature units. So we're left with 31,725 milliliters over 323K. And then it's just a matter of doing that math. So 31,725 divided by 323 equals 98.2. And again, this is a unit of volume, so I want that unit for milliliters. All right, awesome. And again, you guys, making sure that we went through, double-checked, we found what we were trying to find. We converted our temperatures to Kelvin. We used the correct formula. We used our help tool to do it. We needed V1, so we used this formula right here. We understand that this backslash that we see right here is the same as this line right here. That's our division line. Let's do number 4. Chlorine gas occupies a volume of 25 milliliters at 300K. What volume will it occupy at 600K? Well, the first thing I notice is that my temperature units are already converted to K, so this time I don't have to go through and do this process right here, which is nice. So it says a chlorine gas occupies a volume of 25 milliliters. So I believe that is my V1. At 300K, that's definitely my T1. What volume? We don't know. That's going to be our V2. Will occupy 600K, but we know this is going to be our T2. So we're trying to find V2. So V2 equals we're going to use our handy dandy sheet here. Here's V2. It's the third one down in our Charles Law section right here. And we've got V1 times T2. There's that forward slash, which means over T1. Let's go ahead and set that up. So V2 is the same as saying V1 times T2 over T1. Now we can go ahead and plug in what we had. So we determined that our V1 is this 25 milliliters. We determined that our T2 is 600K over T1, which we determined to be 300K. And because of our order of operations, we're going to do our multiplication on top first. So we're going to take 25 times 600, and that equals 15,000. As far as what unit, again, remember, this is a unit of volume, so we can go ahead and cancel out our units for temperature, and we're left with milliliters over 300. So our V2 then, if we take 15,000 divided by 300, that leaves us with a V2, or a volume 2, of 50 milliliters. And that's going to be my final answer. Fantastic. So far, so good. And again, you guys, as you're watching these videos, if at any point you feel like you're comfortable and you're like, yeah, I got this, you know, you can always turn the video off and move on with your life. You don't have to watch the whole thing, unless you want to, because this video is that good. I know better. All right, let's do number 5. It says a sample of neon gas at 50 degrees Celsius and a volume of 2.5 liters is cooled to 25 degrees Celsius. What is the new volume? All right, new volume, you guys, because of that word, we know that context-wise we're looking at a second volume, so that's going to be our V2. A sample of neon gas at 50 degrees Celsius, that's our T1, and a volume of 2.5 liters, that's going to be our V1, is cooled down to 25 degrees Celsius, that's going to be our T2. So right off the bat, I noticed that I'm dealing with degrees Celsius for both of my temperatures. So I'm going to take the time to do my temperature conversions first, because that's what I like to do. So we're going to go ahead and do our T1. So T1 equals 50 degrees Celsius plus 273. So we're going to go ahead and do that. 50 plus 273 is, T1 is equal to 323K. Now let's do that, but with our T2. So T2 is 25 degrees Celsius plus 273. And if we add those up, 25 plus 273 is 298K. And I'm going to go ahead and section that off. And now I've got both of my temperature data that I need for this formula. Now, in terms of what I'm trying to find, I've got my V1 right here. What I do not have is my V2. So I know that's where I'm going to aim myself as I'm trying to figure out which formula to use. Again, using Charles' law right here. Looking for the V2, which is right here, and I'm going to come over and use this formula. V1 multiplied by V2. Got my slash right there, so I'm going to divide by T1. So V1 times T1, or V1 times T2 over T1. Let's write that out. I'm just going to leave that right there so it's close, so I know which formula I want to use. V2 equals V1 times T2 over T1. V1, T2 over T1. Let's plug in and see what we have. V2 equals, my V1 we determined was 2.5 liters, multiplied by our T2, which we determined was, after doing our conversions, 298K, over our T1, which we converted to be 323K. And again, once we do our order of operations, that's going to be 2.5 times 298. And that's going to give me 745. And again, I'm dealing with a unit of volume, so I'm going to go ahead and like, oh, look, there's a unit of volume right there, which means I'm going to cancel out my temperature units. So that's going to be 745 liters over 323. So then my V2 equals 745 divided by 323. And that's going to give me 2.31 And again, you guys, that's going to be our unit right there. And it's a unit of volume, 2.31 liters. And again, you guys, we can always kind of check it and decide if this is a logical answer. Because look what we did. We went from 50 degrees and we cooled it down to 25 degrees. Our original volume was 2.5 liters. So if our temperature decreased, then theoretically our volume should decrease as well. Did that happen? So our original volume was 2.5 liters. Our new volume is 2.31 liters, so it did drop. So this actually makes sense, and it's a good indication that the work we've done here is correct. All right, cool. All right then, let's take a look at number 6. It says fluorine gas at 300 K, ooh, that's nice, it's already converted to K, occupies a volume of 500 milliliters. So right off the bat, we know that we've got a temperature here, we have a volume here. To what temperatures? We know we've got another T, and it's asking to what, so we don't know what that T2 is. Should it be lowered to bring the volume to 300 milliliters? So this is going to be our V2 right here, and up top will be our V1. Now what's nice about this problem is that I don't have to worry about converting to K because it's already converted for me. So let's go ahead and figure out what we are solving for. It looks to me like we are solving for T2. So let's get that up here. And if we look at our document, and again, we are still working in the center of this document with our Charles Law problems, T2 is the same as saying V2 times T1 over V1. There's that forward slash, which means V1. Let's go ahead and set that up. T2, again, using our formula right here, is V2 times T1 over, and that's what that forward slash stands for, over V1. Let's fill in some stuff. T2 equals V2, which we determined to be 300 milliliters, times our T1, which is given to us at 300 K, over V1, which right here is 500 milliliters. So now we can go ahead and do the math. I guess we can do the math. So T2, we're going to take 300 milliliters times 300 Kelvin. 300 times 300 equals 90,000. And remember, as far as our units, we're trying to find a temperature. So that means that needs to be our final unit right there, that K, which means we are going to cancel out milliliters. And that leaves us with 90,000 K over 500. So then T2 equals 90,000 divided by 500, and that equals 180 K. And again, if I wanted to, I could convert this back to Celsius, but we're not going to worry about that right now. All right, number 7. Helium occupies a volume of 3.8 liters at negative 45 degrees Celsius. That is cold. What volume? It looks to me like we are looking for a volume here. Will it occupy at 45 degrees Celsius? All right, so this is going to be our V1, 3.8 liters. Negative 45 degrees Celsius is going to be our T1, and 45 degrees Celsius is going to be our T2. Now, because our temperatures are all given to us in Celsius, yes, we're going to have to do our temperature conversions. Let's go ahead and do that. So T1 equals, now notice, negative 45 degrees Celsius plus 273. So obviously we're going to do a little subtraction this time. So T1 equals negative 45 plus 273. And we end up with 228 K. And like I said, section it off because it keeps things clear for us. As far as our T2 is 45 degrees Celsius plus 273. So our T2, and we can go ahead and do the math on that, 45 plus 273 is 318 K. Fantastic. We have both of our temperature conversions. Now let's figure out what we are solving for. Well, we have our V1 already. What we don't have is our V2, so we know we are going to have to solve for V2. So V2 equals, and we can go back to our helpful sheet if we need to, looking for the third one down, which is V2, V1 times T2 divided by or over T1. Let's go ahead and write that out. V2 equals V1, volume 1, times our second temperature over T1. And again, you guys just using this formula right here. V2 times T1 forward slash, which is another way of saying over, which is another way of saying divided by our V1. Wait, did I mean to put V1 or did I mean to put T1? T1, yep, sorry about that. So V2, let's go ahead and plug in our numbers. Our first volume is 3.8 liters times our first temperature. And remember, we've done our temperature conversions here. This is going to be our T2, so we're looking right down here at 318 K, over our T1, which we calculated to be 228 K. So our V2 equals 3.8 times 318. And we end up with 1,208.4. And again, I'm looking for a volume, so I want to cancel out my temperature units of Kelvin. That leaves me with 1,208.4 liters over 228. So my V2 equals, I'm going to take that 1,208.4 divided by 228, and that leaves me with 5.3 liters. Liters is my unit because it's a unit of volume, and it is the unit I have left up here. Let's see if that makes sense. So we started out, we had this big jump in temperature. Our original volume was 3.8 liters. Our temperature increased, which means our volume should increase, and it does. We go from 3.8 liters to 5.3 liters. Excellent. All right, let's do this last one, number 8. It says a sample of argon gas is cooled, and its volume went from 380 milliliters to 250 milliliters. So we've got two volumes there. This is our first volume, our V1, and this is our second volume, V2. If its final temperature was minus 55 degrees Celsius, so the final temperature, so the T2, what was its original temperature? So if we see the word original, we know we're dealing with a 1. And so in this case, our T1. That's what we're looking for right there. So to start with, let's figure out, do I need to do a temperature conversion here? Yes, I certainly do. So we're going to find our T2. T2 equals minus 55 degrees Celsius plus 273. So our T2, and I'm going to go ahead and do those numbers real quick. Negative 55 plus 273 is 218 K. And like I usually do, I'm going to section that off because I'm me and that's the way I like to do things. Okay. So now that we have our temperature conversion for our T2, remember we're trying to find T1. So T1 equals what? Well, let's go back to our handy dandy little sheet here. And if I'm looking at that center section, I see the T1 right here. And T1 is V1 times T2 divided by V2. That slash mark means over. It means divided. So T1 equals V1 times T2. And again, you know how much I like my parentheses rather than using X's. So V1 times T2 over V2. Let's fill in some numbers. T1 equals volume 1, which is 380 milliliters, times T2, which we figured out is 218 K, over my second volume, or V2, which is 250 milliliters. I'm kind of out of room, so I'm going to go ahead and bring it down here. So T1, we're going to multiply these two together, 380 times 218. And I end up with 82,840. And specifically as far as units, remember, I want a temperature, so I know my units are going to have to be K, so I'm going to cross out my units of volume, and I end up with 82,840 K over 250. So I'm going to take that 82,840 divided by 250, and I end up with 331.36 degrees Kelvin. And there you go. That is my T1. All right, so if you have questions about this, like I said, you guys, I just kind of walked you through this process, and hopefully you have some clarity now about how to use this and what all of these little symbols mean. Just remember, if you see that little slash, if you've got two sets of parentheses right by each other, you're multiplying them together. If you've got that slash, it means divide, so you're multiplying these things together first and then dividing by whatever happens to be under these two sets of numbers right here. Okay. Now, if you have questions, as always, let me know. I am happy to help. Hopefully this was helpful to you, and have a great day.